Welcome everybody. I'm happy to be able to speak at conferences again. I haven't done it for quite some time. So if you're interested in the content of this talk, the talk is online, and I will show this link one more time at the end of the talk, so there is no need to take notes or pictures. But of course, you're free to do so if you want. So a few words about me. I'm currently working as a principal software engineer in the Amazon Corretto team. Who of you knows Corretto? Oh, so all the others should take a look. It's, I would say, one of the best JDK distributions available. Yeah, I'm working on OpenJDK since about 15 years since OpenJDK was established, and I work on Hotspot even longer. I'm an OpenJDK member, committer, reviewer. I'm in various OpenJDK groups, like the build group, the hotspot group, the porters, and the vulnerability group. Since this year, I'm also a member of the governing board, and I represent Amazon in the Java community process in the executive committee. In the past, I worked for SAP on the SAP JVM and Submachine. That's not far from here in Waldorf. Locals may know it. I was a project lead of the PowerPC AX and S390 porting projects, which are now part of OpenJDK. And I was a member of the Java SE expert groups 9 to 13. And like when I prepared this talk, I found out that like 11 years ago, I already was a speaker at EclipseCon 2011, and I had to talk about how to contribute to OpenJDK, so the slides are still online. So now let's get started on the topic. So zlib, zip, deflate, what's all about this? So actually deflate is a compression algorithm. It's defined in the request for comments RFC 9051. And it's a combination of Lampel CIF 77 and Huffman coding. I will show you how this works on the next slides. But zlib is also a library which implements this deflate algorithm. It's a famous zlib library available on www.zlib.net. It was developed by Jean-Luc Gailly and Mark Adler back in 1995. So you see it's about the same age as Java. And zlib is not only the library which implements deflate, it's also another standard, like another RFC 9050, which defines a compressed data format that's basically a deflate stream combined with a Adler 32 checksum. Then gzip. Everybody who uses Unix probably knows the famous gzip tool, which can be used to compress files. So gzip only compresses single files. It's usually used together with tar. Tar collects files in several directories, and then in the end, you use gzip to compress it. And again, that's defined in RFC 9052. And it adds a CRC32 checksum, in contrast to the zlib format, which uses Adler 32 checksum. And then there is zip files, which probably everybody knows. So zip is actually just a container format for compressed files, and like zip can contain directories and files, as many as you want. And zip is actually a quite big specification. It's more than 100 pages. And it supports a lot of additional features like compression or different compression. I wanted to say signing and different compression algorithms, encryption, even encryption. But it's quite old. We will look at some detail how zip works at the end of the talk. So what's the history of zlib and zip in Java? So when JDK 1.0 in 1996 was released, so you see this was just a year after zip and deflate were defined, specified. So the JDK Java 1.0 version supported class loaded from zip files, but only from uncompressed zip files. So as I said, the zip file format allows you to use different compression algorithms, and one of them is like stored, so that just stores the files without doing any compression to them, basically like tar. Only JDK 1.1 in 1997 added support for compressed zip files. It also introduced an API to access this functionality from within Java. JDK 1, Java 1.0 didn't have that. And this Java util zip functionality was implemented by a JNI wrapper around the zlib library, which just had version 1.0.4 at that time. JDK 1.1 also introduced the jar file format, which is basically a zip file with some additional meta information in the meta-inf directory. But there was no API support for that. That was only added in JDK 1.2 in 1998 with the Java util jar package. And then finally, quite some time after that, in JDK 7, 2011, a zip file system provider was added. That's an NIO file system provider, which can be used to mount a zip file as like a file system and then use it with all the NIO file APIs to write files, remove files, delete files, and so on. It's quite comfortable to work on that. Here is the interesting changelog I found in some historic JDK versions. So it's actually still possible to download version 1.0 and 1.1 of Java from the Oracle side, if you follow the link. And you see this is the changelog from changes between Java 1.1 beta 3 to 1.1 final, and now we can finally handle compressed jar files. So that's how it started. So some more details about how the zlib library is integrated into OpenJDK. As I said before, the Java util zip classes use JNI to access the corresponding functionality in the zlib library. And basically for inflate and deflate, so that's like compression and decompression, the JNI overhead is not so big, because usually compression and decompression takes quite some time. So the overhead is relatively small and tolerable. But the Java util zip package also exports the CRC32 and other 32 checksums. And if you use that for smaller text, the overhead can be quite significant. And because of this, the functionality, the CRC32 and other 32 functionality was later implemented as intrinsics. So intrinsics is basically a manual assembler implementation of this functionality, which the JIT compiler knows about, and when it JIT compiles the Java util zip CRC methods, instead of compiling the bytecodes of the CRC implementation, or instead of using the down call down to zlib, it just replaces this call with optimized assembler code. If you're interested in this topic, I have another talk about hotspot intrinsics. You can find it on YouTube, just as a side note. That, like, if you use gzip, for example, in OpenJDK, then it will call the zlib library, and zlib will do the CRC, the Adler 32 computation in zlib. But if you use standalone CRC from Java, it will be replaced by intrinsic, and it will be much faster. So the zip file support, that's actually not in the zlib library. So the zlib library only implements the deflate, inflate algorithm, the zlib stream, and the gzip compression, but not zip file support. That's in the zip tool, pkzip. So zip file support was implemented again as a very thin JNI wrapper over some C functionality, and that used mmap to map the zip file into memory. And that led to a lot of problems when these jar files, which were memory mapped into a Java process, were concurrently modified. That happened quite often. For example, if war files were deployed and then overwritten, or during development when people changed their class paths while Java application was running. So this problem was then mitigated with a property in JDK 6 updates 23 and downport it to JDK 5, which allowed you to disable this memory mapping functionality, but that had some performance impacts. And finally, only finally in JDK 9, this issue was finally fixed by re-implementing the whole ZipFile support in pure Java. And this not only made the whole implementation more stable, but it also resulted in a nice performance boost because you saved a lot of the JNI calls. And there is a nice blog from Klaus Redestad from Oracle about the work that was done there and some benchmarks and performance improvements. So now I want to show you some details about how Dflat works, because that's, first of all, I find it quite interesting because this Dflat algorithm is like defined in about 10 pages, but it's still, it has a big impact on industry and especially on Unix. It's basically everywhere. It's used in the kernel. It's used in HTTP to compress the data stream. It's used in Java. Basically, every language has support for zip or zlib deflate compression. So Dflat, like as I said, is a combination of Lampelt 77 and Huffman coding. So first, let's see what Lampelt 77 is. That's actually a dictionary-based sliding window compression. That means while you're scanning your input text, which in this example is blah blah exclamation mark, you output characters which you haven't seen before, and then when we see the second B, we look backwards and see, oh, we already saw B, but we didn't only see B, we actually also see L and A. So instead of outputting B, we just output a back reference, a relative back pointer that says like three characters back. We had the next three, we already saw the next three characters, and then instead of outputting the next three characters, we output this offset length marker. That's actually how it works. And that already can lead to quite good compression for some data. But as you can imagine, storing of this back reference and length is a little bit more expensive than storing just a single character. That's why it doesn't make sense to store patterns which are smaller than 3. So like Dflat only stores back references to patterns which are bigger than 3. So in this example, again, we proceed, we see these characters A, B, C. Then like for BC, we see there was already a back reference, but it's just 2 characters, so we ignore it. And then when we reach this A, we see we already saw ABC, so we output this back reference length field, like 6 characters back, length and length 3. And then we proceed at D and A. But there is one important thing here. This processing of the data, that's ambiguous. It depends how far we look backwards and how far we look forward. And you can see this here. This is actually the same input text, and we proceed the same way. But here at A, we could output a back reference for the sequence ABC. But if we would wait one more character and just output a literal A, we would see we could find a back reference for a string of length 4. So that's more efficient. And as you can imagine, if you have a huge text file, you have to trade off between computation when you are compressing and the compression ratio which you achieve in the end. And that's exactly what what the compression level is like for zip. For zlib, for the Dflat, you can set a compression level between 0 and 9. So 0 is like the lowest compression level that's optimized to run as fast as possible, but the compression rate is not so great, and 9 is like best compression rate, but might take quite some time, and 6 is the default. So in Java, if you just use zip deflator, it will use 6 as default compression rate, and that's also if you use the zip utility on the command line. So this was about LZ77, but as I said before, this LZ77 doesn't always give you good results because, like, you need a tag to decide if a character is really a literal character or if it starts a back reference. And this means if your back references are fewer than the characters, then the result might get even bigger. So here is another compression algorithm, which is again good for other kinds of text. So it's Huffman coding. That means we try to encode characters which are more often with a shorter code, and achieve compression through that. So there is an input string here. At the beginning, it's taken from Wikipedia, this example. And what we do first is like we count the occurrence of each character. So you see there is 2 C's in the text, there is 6 B's, and so on, 7 E's, 11 A's, 10 underscores, and 10 D's. And then what we do is we choose the 2 characters with the lowest probability. So in this case, that's C and B. And we create a new node in a virtual tree and give this node the sum of the probabilities of the 2 characters which it combines. And then we proceed again by taking the two nodes with the lowest probability. So this is now C, B, and E in this case. And again, we combine their probabilities, 7 and 8, that gives 15. And we proceed this way. The next one is like the 2 is underscore and D because they have now the lowest probability, 10, 10. And then next is 11, 15, A and ECB. And finally, we've constructed a tree for all these characters which occur. And the nice thing about this tree is now that characters which occur most often, like A in this case, you see that has the lowest distance from the root to the leaf. While characters which don't occur as often, like C, they have a much longer path from root to leaf. And we can now match the edges with 0s and 1s, all the edges. And now we can use these 0s and 1s to assign each character a new code. So for C, we would assign 4 zeros. For B, we would assign 0, 0, 1. E only can be reached by 3 edges, so it can be encoded with only 3 characters, 0, 0, 1. A only with 2, and underscore and D again. And this is so-called prefix code, so it means no character is the prefix of another character. So if we have a stream of these codes, by starting at the beginning, we can always read and always deterministically find the character which are encoded. And here finally is the encoded text with this Huffman code. And just to highlight that, for example, underscores are 1.0, and this is the 1.0s in the encoded text. So the great thing about Dflat is now that it combines both the power of LZ77 and Huffman into one compression algorithm. And it does that by creating like a new alphabet of 287 characters. Like the first 255 characters represent the literal bytes. Then 256 represents end of block, and the other characters are used to represent a length. So the codes 257 to 264 they represent the lengths 3 to 10. Then 256 to 268 represent 11 to 18. But you see this is only 4 bytes, and they represent 8 lengths. That's because they use an extra bit from the input stream. So if Inflate reads one of these codes, it knows that it has to use one more character combined with these 4 bits, and then you have 4 bits to encode the lengths, and so on. And it uses another alphabet with only 32 characters to encode the length, encode the offset, the back reference, the distance, and that's a value from between 1 and 32,000. And it uses the same trick, like it only uses 5 bits to encode it, plus 0 to 13 additional bits. And what it does now is it creates a Huffman code of this alphabet with 287 characters, and that results in a very efficient encoding by first doing by using LZ77 and Huffman combined. So let's come to the results. So for a long time, zlib, the original zlib by Mark Adler was the only available zlib implementation. But during the last years, a lot of additional implementations have occurred. Most of them were derived from the original zlib library. Some of them are clean room implementations. And they have achieved quite good performance improvements. So this is like a benchmark which shows the throughput of infrared in kilobytes per millisecond for various files of the Silesia corpus. So the Silesia corpus is just an example text corpus which is used to benchmark compression algorithms. And you see here the ISA-L library, that's the Intel storage library, storage acceleration library. It's quite fast. It's like 4 times, sometimes 6 times faster than the original zlib. So zlib is always 100% in these charts. That's because it takes advantage of all the Intel CPU features like vector instructions, and it's hand optimized, and it's also tuned because it's a clean room implementation. It doesn't offer the zlib API, so it's not easy to use that in Java. You would have to create a new wrapper for that. But all the other implementations, like the Chromium zlib, zlib NG, zlib IPP, which is Intel performance blocks, and Cloudflare version, they are all derived from zlib, and they support the exact same API. So you can basically use this new implementation as a drop-in replacement, and we will see in a few seconds how you can actually do this. And these 2 graphs are the first one is from 2020 and the second one from 2022, and you see that even in these last 2 years, a lot of development happened. So for example, the red one, which is the zlib NG, got a lot faster in the last 2 years. So during 2020, I ordered them from slowest to fastest, and now I kept the ordering, so you can see that zlib NG, for example, has improved a lot, but others as well. And this is all measured at compression level 6, the default compression level. But if you see at this graph, you can see that there is a huge difference based on the compression level. So what you can see here is on the x-axis you have the compression ratio, and on the y-axis you have the throughput. Again, the throughput which we saw before. And now every point in the graph represents a compression level. So you see, for example, for ISA-L library, compression level 0 has a compression ratio, has a smaller compression ratio, but it's very fast. It has more than 200 kilobytes per millisecond. Like compression level 3 is has much better compression level, but it's only half the performance. And this is for a Mozilla. That's a shared library which is part of the Silesia corpus. So this is like a binary file, and you see the characteristics of all these other libraries on the different compression levels, and they differ. And what is most interesting is that for other kinds of text, like this is, for example, an XML file from the Silesia corpus, you see some algorithms are better for some kind of input data and some for others. So this interesting is quite interesting here because you see compression level 3. Also, it takes much more time to compute. It has a lower compression level than 2. So there must be some issue with that algorithm, why it takes so much longer, but still produces not so good output. So depending on your text, if you, for example, know that you're always compressing XML data, it might make sense to choose a different compression level to get the right balance between the time you spend during compression and the compression ratio. And this is the same graph for inflation. So inflation, we don't have different compression levels for inflation. And you also see that the difference is not that high for inflation because there is not so many tricks you can play. Once the file is compressed, like deflation is quite straightforward to decompress the file. But still you can get like 50% improvements, which is in some use cases also might be significant. You can find additional benchmarks. These were all benchmarks for Intel x86, so you can find more benchmarks and also for ARM64 on my website, on my GitHub account. So now how I promised you to show you how you can make use of this performance of this improved zlib version. So, but before I show you that, yeah, so we have to take a step sideways. So dynamic versus static linking. So who of you thinks that static linking is better? Nobody. So you all for dynamic linking, or you're all sleeping already? You will have lunch in a few minutes. Yeah. So I mean, there is a continuous war going on. What's better, dynamic or static linking? But there is actually no good answer for that, and it really depends on the use case. So up to JDK 8, the default for Java was static linking, and libzip is the library which implements the JNI wrapper in the JDK. So if you do an LDD on libzip and grep for libz, you will see that you don't find it in JDK 8 because it just statically links in the zlib library. Actually, the zlib source code is part of the OpenJDK source tree. Like starting with JDK 9, the default for OpenJDK changed. So you now see libzip is statically linked against the system libz. But that's a configuration option. Everybody can build it the way he wants. It's just the default. On Windows, you always have static linking because Windows doesn't have a default system zlib. For example, recent versions of macOS M1 had a buggy zlib, and which didn't work well with OpenJDK. So OpenJDK vendors had to switch their build from macOS back to static linking because otherwise you would get errors. And then there is security considerations. Like when you're using dynamic linking, you basically say, okay, I put the responsibility for maintenance of the library to somebody else, like to the OS system provider or something else, because I just link it. But you might remember that last year or this year, I don't remember, we had this zlib CVE, which many people get quite nervous about. And then a new release was done for zlib 1.2.12, almost 5 years since the last 1.2.11 release. And that broke OpenJDK compatibility. So all the JDKs which were dynamically linked didn't work on systems which had this new zlib. So in that case, static linking was the better choice. So, but as I say, in the end, every OpenJDK vendor decides himself. And for example, vendors which like Red Hat or Amazon, which have Amazon Linux, or Red Hat Fedora also, which maintain both the operating system and the JDK, they of course use dynamic linking. But vendors who have to support many different operating systems, they tend to use static linking because then they are in the control of what they use. So how you can use alternative zlib implementations with OpenJDK? Well, it's quite easy. If your OpenJDK is dynamically linked against zlib, you can just use LD library path or LD preload. LD library path takes a path to an alternative version of your zlib library. LD preload contains the file itself. And you can even check on the running process which library it has picked up. Like the first slide I showed you is LDD, how you can check how it was built. Like by looking at the proc file system in the maps file, you can see that for a vanilla Java process, it picks up the system zlib library. But if I start Java with a LD library path pointing to directory where I've copied in the zlib, the Cloudflare version of zlib, and run the same command, you see that now it picks up this library from the temp directory. And that's it actually. LD preload works the same way. So before I finish, I want to point out that there are a few issues when using these alternative versions of the library. As I said before, the API is exactly the same, but because OpenJDK or Java has used this default zlib for so long time, there is a lot of implicit assumptions in the OpenJDK or in Java code which can now be broken if you use a library which actually still conforms to the standard, but it's faster or compresses better. And one issue is with inflator input stream read, because inflator input stream read is derived from input stream. And input stream read has this specification. It takes a byte for reading bytes into, an offset and the length. And then it says it reads k bytes and into your output buffer, but all the bytes beyond the last read byte will be left unaffected. That's just how it's defined, how input stream is defined. And just by virtual inheritance, inflator input stream has the same specification. On the other hand, inflator input stream calls inflator read. Inflator read is the class which calls down to zlib to do the inflation, the decompression of the data. And inflator read never had this restriction, but it never caused any harm. But inflator read is actually free to scribble, to use the additional place in the output buffer, which is not occupied by the deflated bytes as scratch buffer. Sorry. So with the original zlib, that never happened. But newer optimized versions of zlib do this. And why they do this will be demonstrated here. So during inflation, the original zlib does bytewise copy of the compressed data. So when you look at this example, you have the original text there, and then let's say we have a deflated stream of this original text, and we decompress that. And at the point we find this marker which has like 16 bytes backwards. There is a string which I saw before, and it has length 9. And in the output buffer, we are at this position. It means we will now output these 9 bytes from back of our input stream. That's fine, and that's how it finishes. But zlib Chromium, for example, uses vector load and store instructions to make decompression much faster. That's one of the reasons why it's faster. And when it sees this back reference and length, it doesn't do this byte-wise. It just uses a 16-byte vector load store instruction. And it copies like 16 bytes. It still returns the correct number of decoded bytes. And it will never write past the end of the buffer. But it takes the freedom to use this additional length at the end and write additional data there. So why is this a problem? You might think, well, input stream had this restriction, but I mean, it makes no sense to save some data there, because if you call inflator stream, input stream read or inflator input stream read, you can never know how much data will be written into the output buffer, and it can always be filled completely. So there is no reason to save some data there. Actually, zlib Chromium did even is even worse, because they were aware of these differences. They even put some padding bytes there, so that there were always some bytes, even if the 16-byte load store didn't write additional bytes. They always put these extra padding bytes there to warn users that they behave differently. And actually, this really caused actual code to break. So this is code taken from ASM, the bytecode assembling library. And what it does, it's actually quite nice performance optimization. It reads in a while loop from an inflator input stream into allocated in the data array. And then it remembers how often it called read until no more data was available. And if it only called like read once, then it knows that all the inflated data is in this pre-allocated data buffer, and you don't have to call output stream to byte array, which creates a new byte array. So instead, you can just return the data buffer. But remember that the Cloudflare library puts this extra padding bytes at the end, and even if read count is 1, you call 2 times inflator input stream read, right? You call it the first time, which returns the number of inflated bytes, and then you have to call it the second time to see that your data data in your input stream is at the end. And this second call also does a call down to the zlib, to the native zlib implementation, and that will then just put this padding bytes at the beginning of the data buffer and overwrite the data you've read before. And that led to crashes. And was actually not only in ASM, also Spring, which under the hood uses ASM, crashed with exceptions if they used zlib Cloudflare. And how can we fix this? Well, we fixed this in OpenJDK 19 and 20 by avoiding this second unnecessary down call to zlib in the first place. So that was also, that not only fixed the problem, but also performance optimization. But that's only in JDK 19 and 20. So all the people who use all the Java versions won't benefit from it. So we also fixed it in zlib Chromium by convincing them that it's not a good idea to write these padding bytes. So now they changed it to only write them in the debug build. And interesting enough, while we were doing this fix in zlib Chromium, we noticed that zlib Cloudflare also picked up some of the optimizations from the Cloudflare project, so they also had this problem. So we also had to fix it in zip Cloudflare, which we've done. And another thing which we have done in JDK 20 is to weaken the specification of inflator input stream, to not be as strict as its base class input stream. That was quite a fight because that required an API change, and that's actually a standard change. But in the end, we could convince Oracle that it makes sense to weaken the specification of inflator input stream, and there is a warning now in the API which says that inflator input stream can scribble the bytes beyond the last inflated byte, and that's in contrast to the base class, which doesn't allow that. I have also an article about that on GitHub. I don't know, I think, when is this supposed to finish already, or? I don't know how long this takes. 5 minutes ago. Ah, okay, oh, sorry. So I don't know, I have 5 more minutes. I mean, if you want to go to lunch, please feel free. Like, I just want to have 2-3 more slides about zip file format and how that affects how that is affected by this new alternative zlib implementation. So feel free to listen 5 more minutes or go to lunch. So this is just a small overview of how the zip file format works. So like the highlighted line is basically the zip file, and it's contained of so-called file entries, and at the end of the zip file there is a central directory. It's kind of strange layout, but that's because zip file format was really done for floppy disks, if you remember them. I think some people might still remember floppy disks. And the thing with floppy disks is that if you had a zip file which spanned several disks, it was good to have the central directory which contains most of the administrative data on the last disk, because then you could easily add one more file to the archive. Like when that would be in the first disk, all the other disks would have to be changed to update the archive. And then like every file entry has a local file header, which contains the name of the file, the size, compressed and uncompressed size, the CRC checksum, and so on. And then there is a central file header in the central directory, and that basically has the same data. And actually, the central directory is the main source of truth. But to make it more redundant, it also has the local file header. That could also be used to recover zip files which were partially broken or where the central directory was broken. And then there is also a data descriptor at the end of a file entry, which again contains compressed and uncompressed size and CRC32. That's again for the case where that's an optional, the data descriptor, but when you start writing a file to the zip file, and you don't know beforehand the uncompressed size because maybe you read the data from a socket, for example, you cannot put it in there, right? Also, you don't know the compressed size because you don't know to which size it will be compressed. So in that case, you just put in a 0 there, and then the data descriptor at the end of the file will contain this data. Then data is just a deflator stream, as we've seen it before, and then there is an end of center directory, which is just a marker to easily recognize zip files. So what's the problem here when we use alternative zlib implementation? So zip entry is actually the class which corresponds to a local and central file header in Java. And zip entries are returned either by zip input stream or by ZipFile. So zip input stream always corresponds to the local file header or the data descriptor, while the zip entry returned from ZipFile corresponds to the data from the central file header. But Java has no good way to copy the compressed data stream from an input file to an output file. What you have to do is you have to first inflate it and then deflate it again into the output file. And this is a small example how this could be done. So we have a zip input stream from a source file and a zip output stream. And then we read a zip entry, which is basically the local file header, and put this entry to the zip output stream. And then we call transfer, which actually does an inflate of the data from the input stream and deflates it again into the output stream. So you see what the issue is here. This is not only an issue with new zlib implementations, but the problem is if somebody who created the source zip file used a different compression level or used a different implementation of your zlib library, it might have compressed your data with a different compression ratio than your current compressor, which is used by the zip output stream. But if you write the zip entry from the source file out to the out file, that contains the wrong compressed size, and this will lead to zip exception invalid compressed entry because there is an assertion in the file which checks that the compressed size recorded in a zip entry or in the local file header corresponds to what it actually generated. And again, if you search for this exception, you can find quite some occurrences on Stack Overflow and in Google, but it was not as much of a problem in the past because most people used the zlib, the original zlib, and they always used the default compression level 6. So only when people started experimenting with different compression levels or different zlib implementation, they started to run into this problem. So again, we fixed this in JDK 16 by refining zip output stream put next to always recalculate the zip entry's compressed size after it was written. So we basically ignore the compressed size value in zip entry until it was explicitly set by the user with the zip entry has a put compressed size method. And again, this required a change in the API specification, and that's why it cannot be downported to older JDK versions. This change actually leads to the case that it will output an empty local file header and then put the right compressed size into data descriptor at the end of the file. Okay, so thanks for bearing with me this long. This is just references. If you're interested in this topic, these are interesting blogs or docs on the topic. I specifically like the last one here, infgen. So that's actually a disassembler for zip files that really outputs all the Huffman codes and the back references, like every single bit which is encoded in a zip file will be output in like disassembly in a way similar to a disassembler, and that's written by Mark Adler himself. So if you're interested analyzing this, you can take a look. So as I promised, this is one more link to the slides, and with that I finished. I think much too late, but yeah. So that's it. Thanks a lot for staying so long with me. I'm also happy to take questions, but we can also do it at lunch. So yes, please.
Do you know why there is a ZipFile and a gzip for stream, but no tar stream or tar file?
In Java?
Java, under Java.
I don't know. I think they probably choose zip files because they were multi-platform already at that time, while tar was Unix only. So that was probably one of the only reason. But I still find it interesting that they choose to bundle zip 1996, because at that time zip was really only a year old. So, but you see how to say, they were quite open to new things at that time. So now after 20 years, it's very hard. I actually proposed to change OpenJDK to allow it to use different libraries for inflation and deflation, because you saw some libraries are better for inflation, some for deflation. There's not the best one for both. For example, Chromium is heavily optimized for decompression, because that's where it is used. It's the Chromium zlib is used in Chromium and in Android. And what they mostly do is they read compressed data from a web server and decompress it. Or they decompress PNG files or GIF files, which all use this compression. So they invested in that, whereas Cloudflare, they store a lot of files, so they invested in improving compression. But unfortunately, OpenJDK didn't want it to take these changes. They said support for one library is enough, and you can use LD library paths. Like, yeah, I mean, there is still a pull request out there in the JBS issue, but I don't think it has any it will be accepted anytime. So yeah. So one more question, or I will be here all day until the evening, and probably tomorrow as well. So you can also catch me. Okay. So thanks a lot, and bye. Have a good lunch.